Sometimes the audio gets jacked up and you got to stop it and do it again, and it always works the second time. So, all right, hey everybody, here's number 12 from the review because people asked about it. You ready? Yep. Hooray! Okay, so here we go. A 0.4 kilogram glob of clay is fired horizontally at a 1 kilogram block of wood suspended by a rope from the ceiling. The clay sticks to the block, which swings in an arc, rising 0.6 meters above its lowest position. Then there's a bunch of questions. So first of all, let's get a handle for what's happening on this. So the first thing is, at the beginning, you've got a block of clay. Yes, I can do this. I'm going to call that C for clay. And it is moving at some velocity, right? And it is going to hit a, what is it, a block of wood? Yeah. We can call that B for block. All right, so that is our first drawing, right? Let's call this drawing number 1. So that is important because this is what's happening immediately before the collision between the clay and the block, right? Drawing number 2 is what is happening immediately after the collision. So here's drawing number 2, immediately after the collision. Now I've got a block of wood with a glob of clay stuck to it. Cool? And then drawing 3, is it going to let me? There we go. Cool. There's drawing 2. And then in drawing 3, the whole system swings up, clay block, to a height of 0.6 meters. All right, so first of all, do we understand the 3 drawings? Yeah. Are there any questions about what's happening in each of the 3 drawings? Does it make sense why I chose those 3 points to focus on? Yes. Okay, so here's the deal. So this year, we've now learned a whole bunch of different sort of like tools that we can use to solve problems. But if you categorize them, really, there's basically 3 categories. I guess 4. Okay? So kinematics, right? 1 half AT squared plus BIT, all those equations, right? So that's describing motion. So that's one category of problems that people tend to do. There's net force equals net force, right? Where you're dealing with using your forces to find out information about the acceleration, right? So that's sort of the second category of types of problems, right? After we finish dealing with forces, we started learning about energy, right? Sometimes your energy is conserved, sometimes it's not, sometimes work is done, blah, 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 blah. So that's another category of problems that we've learned how to do. In this chapter, we've been dealing with momentum. So those are the 4 sort of, categories of problems that we've learned how to solve, okay? So as we start to learn more of these, your first thought should be, which of these categories, which of those 4 categories am I going to use to solve the problems? All right, this one deals with 2 of them. Okay, so let's talk about what's happening. So let's go, as you go from drawing 1 to drawing number 2, which of my categories of tools am I going to be using? Is this about kinematics, forces, energy, or momentum? So if it was about kinematics, we would be dealing with information about like starting velocity, ending velocity, acceleration, that kind of stuff. The fact that you've got an interaction between 2 objects should be a really big key, right? Anytime you're dealing with 2 objects exerting forces on each other and you're interested in the motion of both of them, that's momentum. Okay? This 1 to 2 is dealing with the collision between the glob of clay and the wood block. As soon as you hear the word collision, you should go momentum. All right? So to figure out what's going on from drawing 1 to drawing 2, I should be thinking, oh, my total momentum in drawing 1 has got to equal my total momentum in drawing 2. Does that make sense? Okay. Then, what's happening from drawing 2 to drawing 3? Is it still about two objects colliding? No, the collision has already occurred now, right? Okay, but after the collision, it swings up until it stops, right? So now which of our categories are we dealing with?
Energy.
Energy, right? Because you're right after the collision, the block and the clay have kinetic energy, and then it swings up, you convert that kinetic energy to GPE until it stops. So this is about my mechanical energy in drawing number 2 equals my mechanical energy in drawing number 3. Does that make sense?
Yes.
So, now we just got to solve it. Okay? So, our question is, what was the velocity of the clay beforehand, right? What else do we know? I feel like we have to know more information here. What else does it tell us? Does it give us some masses, I hope? Yes. I know. Oh, that's the wrong problem. I know that the mass of the clay is 0.4 kilograms. And I know that the mass of the block is 1 kilogram. And I know it goes 0.6 meters above the position. Okay, cool. So, ultimately our goal is to find the velocity in drawing 1. So, since we're looking for the velocity at the beginning, let's start at the end and work back. Follow? So, I know that the mechanical energy in drawing 2 is equal to the mechanical energy in drawing 3. So what type of energy do I have in drawing 3, you guys? GPE. So the gravitational potential energy in drawing 3 is equal to the kinetic energy in drawing 2. Good? All right. So kinetic energy, that's mass. What mass am I talking about here, you guys? The whole system. So the clay and the block. Times G times the height equals the kinetic energy in drawing 2. So 1/2 times the mass of, again, the whole system, right? Because after the collision, the clay and the block are now stuck together. So this is mass of clay and block times the velocity in drawing 2 squared. Why am I happy? The masses cancel. So I can now solve for V. And what I discover is that the velocity in drawing number 2 is a number equal to the square root of 11.76. Let's see. So I got to multiply both sides by 2 to get rid of the half. 2 times 9.8 times 0.6 is 11.76. Square root gives you 3.43. Don't forget the smiley face. Are there any questions regarding how I found the velocity in drawing number 2? Let's put it in the drawing. The velocity in drawing 2 is 3.43 meters per second. Okay, cool. Now what? Is it? I don't know. I didn't read the question because I'm not very smart. Hey, what was the velocity of the clay immediately before hitting the block? No. Darn it. That's the velocity of it immediately after the collision, right? Good? All right. So I've done the blue part. I've done from drawing 2 to drawing 3. Now I got to continue working backwards to figure out what was going on in drawing 1, right? Follow? So let's do it. Here we go. From drawing number 1 to drawing number 2, I know that the total momentum in drawing number 1 has to equal the total momentum in drawing number 2. Talk to me about the total momentum in drawing number 1. Well, it's the mass of the clay times the velocity of the clay, which is what I'm trying to find, right? Plus the mass of the block times 0, right? The block starts at rest. So I don't even need to worry about the block for drawing 1. Does that make sense? Equals the total momentum in drawing 2. So mass of the clay times 3.43 plus mass of the block times 3.43, or you can cheat and just combine them and treat the clay and the block as one block, you know, with a mass of 1.4 times 3.43. So we've got a 1.4 kilogram system now, traveling at a velocity of 3.43 meters a second. And to be clear, this is the clay plus the block combined. I didn't skip a step there. Honors physics teacher Mr. Hecker is angry at AP physics teacher Mr. Hecker for taking that shortcut. But do you understand what I did there? Yeah. Awesome. Okay, so now solve it. And now I know the velocity of the clay, and that first drawing is whatever all this is when you divide by 0.4 and multiply by 1.4. I will do it using this calculatrix. It gives you 12 meters per second. Don't forget the smiley face. Are there any questions regarding what I did there? Okay, cool. Question B says, how much kinetic energy was lost? Well, find the kinetic energy before the collision, find the kinetic energy after the collision, and find the difference. Good? Let's do it. Oh, I lost my thing. So, kinetic energy in drawing number 1. That's 1/2 times the mass of the block of clay. Oh, try again. 1/2 times the mass of the glob of clay times the velocity, which was 12. Don't forget to square it. So you get 144 times 0.2 is 28.8. Is that right? I did that in my head. So there's the kinetic energy in drawing number 1. Any problems with how I got that? Kinetic energy in drawing number 2. That's 1/2 times the mass. What mass should I use? 1.4, because that's how much mass is moving, times the velocity. Don't forget to square it. That gives you a number that is less than 28. I will calculate that now. 0.7 times 3.43 square 5. That gives you 8.2 joules. How much was lost? Subtract. You get what, 19.8? Follow? I am a big fan of question C, and last year a ton of people got it wrong, and I was really sad. Question C. Are we good with A and B before I do C? Question C. Which, if either object, has the impulse with the largest magnitude? There are a bunch of ways of solving this, and they should all yield the same result. What do you guys think? Which one has a bigger impulse? It's asking which object, during the collision, which, if either, has the largest... Oh, do you know? Ooh. It does not explicitly... I remember this now, that there was an issue with this last year. Shoot, I need to reword that. All right, I'm going to rephrase the question because I now realize it's worded badly, and I'm thinking ahead of myself. During the collision, from drawing 1 to 2, which one has the bigger impulse? That is a better phrased question. What do we think? All right. Forget about this for a minute. Well, don't forget about this for a minute. Oh, wait, what? Ooh. It is the same. It is the same. Because what is true about my total momentum in drawings 1 and 2? It stays the same, right? So during the collision, my glob of clay loses some momentum, right? That's my change in momentum. That's my impulse, right? Because that's the definition of impulse, right? Change in momentum. So during the collision, block C loses X units of momentum. Well, where did it go? To the other object, right? So whatever's lost by one has to be gained by the other, right? So change in momentum, the impulse is the same for both objects, except for one's positive and one's negative. Mathematically, it's because your change in momentum is both blocks exert the same force on each other for the same amount of time, right? Newton's third law says the forces are equal for the same amount of time, so you have to have the same change in momentum. Cool? All right. Questions on that?
So how do we find the impulse then?
It's just mass times change in velocity. So pick one of the two objects. I guess it would be easier to do it for the block, because the block goes from a velocity of 0 up to 3.43, and then times 1. Follow? You could also do it for the clay, and it would give you the same number, but negative. Cool? All right. All right, well, while we're talking about it, how about from drawing 2 to 3? Which one is the bigger impulse from drawing 2 to 3? Which one has the bigger change in momentum, the bigger impulse from drawing 2 to 3? The block or the clay, or are they the same again? What's the definition of impulse? Mass times velocity is momentum. Definition of impulse is change in momentum, right? So mass times change in velocity. Aren't both things going from 3.43 to 0? They both have the same change in velocity, but not the same mass, right? So the one with the bigger mass is going to have the bigger change in momentum. Because the block is a mass of 1 kilogram and the clay is only 0.4.
Well, yeah, but they're stuck together, so it's going to be considered as
In this instance, no, because it's asking you which of these two objects has the bigger change in momentum. So you have to think about it separately.
But then, sorry, but then for like the first question that you asked, between 1 and 2, how come they're considered the same if they're both two different masses?
You mean when I did the calculations?
Like when you asked.
When I did this, when I said AP, Mr. Hecker is mad at honors, or other way around? Here. What I probably should have done here. This is really, thank you. It's really the clay times 3.43 plus the wood block times 3.43. And I just.
Yeah, before the when you say like before you were saying like the impulse between pictures 1 and 2 is the same for both the block and the clay. Well, how come the impulse isn't the same for the block and the clay between pictures?
Because it's a different scenario. So between drawings 1 and 2, the only force is the force of the clay pushing the block and the block pushing the clay.
Right.
Okay, so all of the forces are internal from drawing 1 to 2, which is why our total momentum stays the same. Okay, why do you agree that the momentum in drawings 2 and 3 is not equal?
Yes. Yeah. Okay.
Why? Why is it not equal in drawings 2 and 3, guys? Well, but what causes momentum to change? Yeah, Diego. Right. Well, okay, so that's your energy explanation, but talk to me about the momentum. Why does the momentum change? Well, so it has already happened.
Yeah.
Why is the velocity changing? That's energy. You're right, you're right, you're right. But when we talk about what... Oh, somebody said it. There's an external force, right? Gravity. Right? While it's swinging up, gravity slows it down. So you've got a net force now. And that net force causes your momentum to change. Follow? So in drawings 1 and 2, there is no net force because all of your forces are internal. So your total momentum stays the same. But from drawings 2 to 3, now gravity has an opportunity to take effect, and that changes the momentum. Yeah.
So like this is just like a hypothetical example. if it wasn't speeding, they just started moving forward, the momentum would still be the same because it's not.
If it was on like a frictionless surface or something, then yeah.
No extra
Yep.
force. Okay,
Yes.
got it.
Huh. No, that's good. That was a good conversation. I'm glad we went through all that. That's important. Are we good, you guys, or no? Okay, so that was number 12. Let's take a look and see what else we need to talk about here. So that was 12. That was definitely our big winner on the survey. We got a little bit of interest in number 3. Ooh, 19. All right, 19, if I remember right, it's almost the exact same problem. Yeah, 19 is very similar. Okay, it's the same thing. The weight swings down and you convert GPE to KE. Then there's a collision and your momentum is conserved. And then it swings up and you're, oh, well, you scared the chewies out of me. I know I heard you knock, but I didn't see you walk in. So I was, thanks. I looked down and there was nobody there, and I looked up and she was right there. Okay. So anyway, 19 is almost the exact same as 12, so I don't think it makes sense to spend time on that right now. So let's run through number 3 real fast, because it will be real fast. So number 3, here's the deal. You've got a hunter. He's mean, he's got a gun. Urgh. He's wearing a little hunter's hat. One of those little hats. All right, there he is. See how mean he is? All right, here's the bear. I apologize if my political views are bleeding through my drawing. What do we got? Totally lost my train of thought. Okay, so what happens is they're holding onto a rope or a pole or something. Yeah, and the bear pulls the hunter. Okay, so action: bear pulls rope, rope pulls bear, right? And since the hunter's at the other end, that means the rope is going to pull the hunter, and the hunter is going to pull the rope. All of those are internal forces, right? So what is the net force on my hunter, rope, bear system? 0. Oh, well, that means that the acceleration of my hunter, rope, bear system is 0. That means the velocity of their center of mass has to stay constant, right? So if initially they're just standing there, and then the bear's like, oh, hunter, and he pulls on the rope. So before he pulls the rope, here's their center of mass, somewhere over here by the bear, right? Right? Does that seem like a reasonable place for my center of mass? All right. Because my net force is 0, that center of mass can't move. So where do they have to meet when they drift in towards each other? At the center of mass. So all you have to do in number 3 is find the center of mass and figure out how far away it was from the hunter's initial position. Does that make sense? So if this is the position of your center of mass, then the distance the hunter is going to move is that distance there. Does that make sense? So how do you find the position of the center of mass? Well, usually the position of center of mass is the mass of the hunter times the position of the hunter plus the mass of the bear times the position of the bear over the mass of the hunter plus the mass of the bear, and solve it, right? Follow? That's it. Good? Questions on it? I need to find somebody in the CIC who can make me a little winch that will pull 2 carts together so I can show you this. Is anybody in CIC this year? Are you really homework?
I'll talk to Trey.
We got little carts.
2 carts.
Yeah, and just like a little motor that pulls them towards each other. So if you put the motor on one cart, you know. Cool. Questions on this? All right. What else? What else? What else? That was kind of, I don't know. So 4 and 11 look like they're our next. Oh, and 15. 4, 11, 15. 4, 11, 15. 4 is center of mass. 11 multiple choice. I don't want to worry about that one right now because I don't know. Because yeah, and then 15. Let's do 15 real quick, and then I'll go back and talk about 4. 15 is this. So what you're trying to do is you're trying to find the position of the center of mass. Okay? So what you need to do is you need to break your mass up into uniform objects, right? Okay? So for this one, you've got the shape, the density is kind of the same everywhere. So split it up into 2 chunks. So if I do this, then the center of mass of that is going to be at the geometric center, which is at a position of 6, 2, right? Cool? And the other one, this top chunk up here, its center of mass is at a position of 2, I don't know what's halfway between 4 and 18, 11. Good? Did I lose anybody there? All right. So now I know the positions of the center of masses. Now I need to deal with the masses of each of those chunks. So do you guys remember what's the trick? It's proportional to the area, right? So you can use your area as your mass, right? And basically what you're doing is you're using a unit of mass equal to 1 square unit of area. Follow? So like if this is in centimeters, right? So let's call M the mass of 1 square centimeter. Oh, in that case, this top chunk has an area of 14 times 4 is, what, 56 square centimeters? And this bottom chunk has an area of 48 square centimeters, right? Yes.
Where'd you get the
It's halfway between 8 and 14. Isn't that the average of 18 and 4?
Oh, okay.
Right?
Yeah, okay.
Does that make sense?
Yeah.
Okay. Okay, so now you just do, so to find your x coordinate, you're going to do mass times position plus mass times position divided by total mass. Follow? And then repeat that same process for your y-axis. Good, is that, do you guys need me to write out more? I'm happy to if anybody wants me to. Are we good?
Yes. You don't have to sell it.
No, you're okay. So if you want to do your x-axis, you're going to take the mass of the bottom particle, which is kind of like 48 square units worth of mass, times the x position of that, which is 6, right? You go to that, Krista?
Yes.
Plus the mass of the other one is 56 square units, times its x-coordinate is 2, over your total mass, so 48 plus 56. And that gives you the x-coordinate of your center of mass.
Okay.
And to find the y-coordinate, you do the exact same thing, but use y-coordinates instead of x-coordinates.
Okay.
No, you're fine. I'm glad you're asking questions.
So like,
Why we're
when you
here.
got the chip column, when you did between 4 and 18,
Mhm.
so you're basing it based off like the block that you drew, not where it actually.
So what I did is I broke my shape up into geometric shapes, and I arbitrarily decided I'm going to call that one chunk. All right, I've now accounted for all of that mass. And here's another chunk.
Okay.
Cool?
Yeah. I guess my confusion was coming from like, based on like the origin for like the 0,0 coordinates, like it's.
Yeah, so the idea is vertically, are you worried about the 11? Is that still what's messing you up?
Yeah, that's like, because I was thinking.
Okay.
I don't know.
So this is a position of 0, right? So just looking at the green chunk, the vertical position of the green chunk spans from 4 to 18, right?
Right.
So where's the point equidistant between 4 and 18?
11.
11.
Okay.
That represents then the center of mass of just that top chunk.
Okay, awesome. Got it.
Cool?
Yeah.
And it's 11 units above our origin.
Okay.
Good?
Yeah, good.
Cool, you guys? All right. We have 7 minutes. I was really hoping that I could do one more of those linear density problems, because I know some of you guys are still struggling with those. Don't think we have time to get through it, though, and do it proper service. Let me do this. Let me run through number 4. Wasn't that the linear density one? Is that right? So this morning I wrote up an answer key to one of these, and it's like 2 lines. Like so much of kind of every time I go through it, explain it. So much of it is about like, here's what this means. Here's why this is this. Okay, and I've gone through that a bunch of times. If you're still not there, let me at least show you all of the work just in one, like, here's what it is, okay? And worst case scenario, you can memorize it. It's not ideal, but it'll at least get you through the test tomorrow. And as you spend more time in your calculus class, you'll learn it and understand it better. I did this last hour with students in 4th hour because I spent more time at the front and I did a breakout session, and I did this. And then I went back and answered questions, and I think everybody left like, oh, this finally makes sense. So I can at least give you the first half of that explanation. And then if you want the second half of the explanation, I'm around after school, I'm around before school in the morning. Follow? Okay, so let's do that then. So I'm going to do number 4. I'm going to find that center of mass. Follow? I don't know what you wouldn't follow there. Okay, so here's what we know in number 4. We know that the linear density of the thing is 0.3. Is it x or x squared? Or am I doing the wrong problem? Oh, 0.4x. Gotcha. Sorry. And you know that the length of the rod is, you know what I can do is actually hold this in my hand. And then I would need to keep walking back and forth. It's 1.8 meters. All right? So, question A says, find the mass of the rod. I'm going to put little feet on my capital M's so that you can tell they're capitals. Cool? All right, so here's how you do this. Mass is the integral from 0 to m dm. Huh, that is useless. So what is dm? Well, remember, you guys, lambda is dm dx. It's the mass per unit length. So if you algebraify this, you get dm equals lambda dx. So what I'm going to do is I'm going to substitute, I'm going to replace dm with lambda dx. Okay? So let's do that first. I'm going to write my integral. I'm not going to put in my bounds of integration yet. So I'm going to just replace dm with lambda dx. Good? So now, though, to solve this thing, over here what I'm doing is I'm adding up little chunks of mass until I accumulate the whole mass of the whole bar. Okay? Because I'm dividing it up into little chunks of mass. Here I'm dividing it up into little chunks of length. So how much length do I need before I accumulate the whole bar? 1.8 meters, right? Good?
Can you just say this out?
Yeah, you can call that L. Yeah. It's the same, I mean, L and 1.8 and this one are the same thing. All right, so now I can substitute, I know what lambda is, right? So this is the integral between 0 and 1.8 of 0.4x dx. And take your integral and you're done. So what's the integral of 0.4x, you guys? 0.2x squared. You got to evaluate it at 0, evaluate it at 1.8. Plug in your numbers. So 0.2 times 1.8 squared gives you a number. What is it? 648 kilograms. That's part A. Good? Questions? All right. Part B wants to know where is the center of mass. So, position of center of mass is the integral from 0 to m, not of dm, but of x dm. Oops, I forgot to put my feet on my m. Good? So it's the exact same thing now. In the same way before I replaced m with lambda dx, I'm going to do the same thing here. I'm going to replace dm with lambda dx. So this is the integral from 0 to capital M of x times dm, which is lambda dx. Oh, shoot, but I made a mistake. What did I do? I'm no longer adding up chunks of mass. I'm now adding up chunks of length. So I got to change my bounds of integration. I got to go from 0 to 1.8 because that's my length, right? Follow? All right, so now I'm going to substitute in lambda. It's the integral from 0 to 1.8 of x times lambda, which is 0.4x dx. X times 0.4x is 0.4x squared dx. Take the integral. So we're going to divide by 3, right? So you get 0.4 over 3x cubed from 0 to 1.8. Good? And solve that and see what that gives you. And I just realized I did something sloppy with my notation here, but we'll fix it in a second. So 0.4 divided by 3 times 1.8 cubed gives you 0.7776. Good? All right, here's what I just realized, though. What I did that was sloppy is my equation is wrong. So this, when you find the position of your center of mass, it's this whole mass divided by capital M. Whole mass divided by capital M. Whole mass divided by, or whole mass divided by capital M. So each of these things should have been divided by capital M. And then at the very end, divide by your total mass, which you know because you found it in part A. I'm around after school, I'm around before school. Let me know how I can help you. Yes, I'm going to stop talking so loud.
For number 7, I thought, isn't force the derivative of momentum?
That's a sneaky question. The question doesn't ask.
The momentum.
Oh, wait. Oh, sorry. Oh, it's not giving you the equation for momentum. It doesn't say the momentum is. It's changing. So that is yes. Yes. Yes, I need to stop recording. I will do that now, and I will post it before the end of the day. What's up, Daniel?
When are the test questions due?
When do you want to turn them in?
I've never came back and got my test.
Oh, okay. Well, then not Friday.